everybody, and welcome to the next webinar by QControl on automated closed-loop hardware optimization for quantum devices. I'm Michael Hush. I'm the Chief Science Officer here at QControl, and today I'm with...
Hey, Michael, and hello, everyone. I'm Yuval, and I'm the lead quantum automation scientist at QControl.
Yeah, it's great to have Yuval here today because he's been really leading a lot of our efforts in automated optimization, which is going to be the topic of this presentation. So today, we're going to go for just under an hour. There'll be a variety of opportunities as we're going through this presentation for you to ask some questions to us, but we ask that you put it through the Q&A function rather than the chat. That way we can see where these questions are and answer them one at a time. At the end of the presentation, you'll get an email which will give you a couple of options. First of all, it'll have a survey, which we'd really appreciate if you filled it in. Not only does it help us better understand how to improve these webinars in the future, it also gives you a chance to get a $50 Amazon gift card. So it's well worth your time. And then finally, that email will also have a link in it to set up an opportunity to talk with us on a call if you want to hear more about what we talked about today or have any other questions about our products here at QControl. So I'm just going to start up a poll to get to know you guys a bit better. Excellent. So there's a poll now, which if you could fill in and just tell us a little bit about what you've been working on in the past. So the actual presentation itself, we're going to split it up into 3 sections. The first section, we're going to introduce the new feature in Boulder Opal, which can be used to do closed loop automated optimization using our cloud services, and show you how you can combine that with mloop, a nice open source package, which makes the integration into your particular experiment a lot easier. In the second section, we'll then give a series of examples of how you can use this automated optimization feature to improve performance of quantum experiments that are relevant to quantum computing, quantum sensing, and communication. And then finally, we'll have a section giving a preview of our latest results where we've used automated optimization to improve the performance of 2-qubit gates on IBM-Q. So I'm still getting a few people putting in their votes on the poll. I'll give you a couple more minutes there. Great. So Yuval, do you want to have a quick...
Yep. So let's quickly review the results of the poll.
Go.
All right. Okay, so the first question about the area of interest. I see most people are interested in performance of quantum computers, improving the performance of quantum computers. So that's great news. I think you'll find the methods and tools we'll present today quite helpful for that.
You're definitely right.
Indeed. Yeah, the second question was about quantum hardware access. So I see that most of the people, they have access via the cloud, which is very relevant. Actually, the results that we'll show today were achieved via cloud access. Definitely some people have direct access, which is even better. And I think also for people without any access, I think you can find interest in many of the features that we'll present today. And the last question was the level of automation. So I see that, well, some people even know mloop. So that's nice to know. Most people with access, I see, use manual calibration. So I think our tools can make your life much easier. So hopefully you'll find it interesting. So yeah, Michael, the ball is in your court now.
Excellent. So yeah, let's start the first section of our presentation. And again, if you've got any questions, put that in the Q&A section. Welcome to QControl's presentation on automated closed-loop hardware optimization of quantum devices. Today, we are going to show you how you can rapidly optimize your quantum hardware in the presence of environmental noise, without the need for a detailed physical model or manual intervention from an expert. This new capability is available right now in our product Boulder Opal. We believe it will become an essential tool in your quantum control problem-solving kit. We are currently at the start of a quantum revolution where a new set of technologies are being developed that will change the way we solve problems on computers, sense the world around us, and communicate. All of these upcoming quantum technologies have something in common. They exploit a phenomenon called quantum interference to function. Creating a device that exploits quantum interference requires pushing our current knowledge of engineering and control to its limits. Some devices need to operate near absolute zero with exceptional temperature control. Some need to be completely isolated from their electromagnetic and vibrational environment. And some involve new materials we have only just discovered. In all cases, our understanding of the physical model that underpins these devices is sometimes incomplete, and there are always noisy processes which affect the performance of the device. The historic solution to these challenges is to come up with manual calibration and tune-up procedures which allow the device to operate for a short window of time before the noise and uncertainty builds up again. Here at QControl, we've asked ourselves, can we do better? The answer is yes, through closed-loop automated optimization that leverages recent advances in machine learning. Today, we're going to introduce to you our new features in Boulder Opal that can be used to automatically optimize quantum hardware without the need for expert human intervention. Our closed-loop hardware optimization feature does not require a physical model of the quantum experiment you want to improve. All you need to do is give QControl's machine learning-based autonomous agent control of your quantum science experiment. The agent will then determine a set of test parameters to be executed on your quantum experiment, perform measurements autonomously, and then use the results in order to determine what to do next in order to minimize a cost function that quantifies the quality of the outcome. For example, if you wanted to optimize a quantum gate on a quantum computer, the parameters would be the amplitudes for the segments of the pulse, and the cost return would be the infidelity of the realized gate, compared to the target gate you want to achieve. This approach to calibration and control design has a few important advantages. First, it does not require a physical model, so it is naturally robust to noise and model uncertainty. Second, our autonomous agent picks points to test based on an intelligent machine learning algorithm. This allows the agent to rapidly find the optimal set of parameters. Third, the autonomous agent can discover novel control strategies that can be more efficient and effective than human-designed ones, because they are directly derived from the device itself. The final advantage of Boulder Opal's automated optimization engine is its managed cloud compute infrastructure. We have optimized our implementation of the autonomous agent so it runs with a 10x reduction in time to solution compared to an implementation on a local machine. Furthermore, we have provided an integration with mLoop, the machine learning online optimization package. mLoop provides a simple way to manage experimental data in an autonomous optimization and allows you to interface with experiments through a variety of validated approaches. Combining mLoop and QControl's cloud algorithms allows you to rapidly deploy and optimize your experiment. mLoop is an open source automated optimization package that was initially developed by myself and Harry Slatyer, both at QControl. Further contributions have been made by Leonardo Andrea de Castro, Brad Momers, Etienne Woody, and Zachary Vendiro. The contributors now on staff at QControl are highlighted in purple. mLoop has already been used on a variety of quantum science experiments, ranging from neutral atoms to silicon, superconducting circuits, and photonic systems. We will highlight some of these applications later in this presentation. mLoop provides an easy-to-use front end for optimizing quantum devices. It has multiple interface options, from file polling to direct integration with Python, and has built-in data management and visualization tools. There are many users out there already using mLoop who can now benefit from integration with QControl's optimization package. Combining mLoop with Boulder Opal's managed cloud compute resources is as simple as installing another Python package on your computer. This integration gives mLoop access to Boulder Opal and its cloud-accelerated computation infrastructure. If you already use mLoop, integrating QControl's Boulder Opal will immediately allow you to see acceleration in your experiments, even using the standard mLoop machine learning algorithms. If you're new to automating your experiment, you have two options. One is to use mLoop as an experimental interface which calls Boulder Opal's autonomous agents, or you can manually integrate Boulder Opal directly into your experiment. The advantage of using mLoop is it's quicker to integrate and you get data management all automatically saved by mLoop. Boulder Opal will then provide accelerated autonomous learners based on Gaussian processes and deep neural nets. Alternatively, if you want more flexibility than afforded by mLoop, using the QControl Boulder Opal automated optimization package alone gives you access to a broader range of agents, a new cross-entropy feature, and the ability to batch experiments, which is particularly useful when accessing cloud quantum hardware. QControl provides example integrations using both strategies in our automated closed-loop optimization user guide available from docs.qcontrol.com. Using either QControl's Boulder Opal directly or mloop combined with Boulder Opal gives you significant performance gains over using mloop alone. We show this explicitly in these plots. A series of closed-loop automated optimizations were run using mloop and Boulder Opal, and finally using a flexible custom Boulder Opal integration. After each optimization run, the optimal parameters were found that resulted in a cost under a set threshold. Here we can see using QControl's cloud infrastructure gives over a 10x improvement in terms of the wall time the autonomous learner took to calculate the next points to test. Furthermore, using Boulder Opal integration directly allows you to take advantage of the batching feature. This allows you to significantly reduce the number of experiments sent. Again, here we see over a 10x reduction in the number of experimental batches set compared to mloop. In either case, integrating QControl's Boulder Opal into your automated optimization gives you a critical advantage in both the speed of the autonomous agent and reducing the number of experiments you run. In the next presentation, we will look at applications of closed-loop hardware optimization to quantum experiments that have applications in quantum computing, quantum sensing, and quantum communication.
Right. Yeah, thanks, Michael. So I see that we already have a few questions. So I see several questions about the cost function. So how do you define the cost function? What is the cost function used in the loop?
Yeah, so the cost function, ultimately, you can define it however you want. It really depends on the specific application you have. In the later presentation, we'll talk a bit about how we defined it for optimizing a quantum computer, because in that particular case, you do have to basically come up with a method for efficiently determining the fidelity of your gate that you're trying to implement if you're trying to come up with a particular gate implementation on a device. And so you normally have to use tricks like repetition and a weighted sum or something like that to define your cost function. But in general, defining a cost function is sort of, there's a certain art to it where you really want to figure out and come up with a number which really quantifies accurately the quality of the outcome you want. But we've got a bit of experience with this. So if you want to get some advice from us, we'd be happy to. So please come talk to us about your particular device and what you're trying to do.
Yep, and maybe I can just add to that for canonical or frequent optimization problems, we can do the heavy lifting and provide a good cost function. And I guess for users that are interested in more exotic problems, probably they'll need to define their own cost function. Okay, let's go for more questions. Which data do you use to feed your ML routine?
Yeah, so when you're actually doing the experiment, the required data is the parameters that are controlled by the experiment and the cost function with basically the cost value that you measure, plus you can provide optionally some uncertainty associated with that cost. So we do actually recommend that you provide that uncertainty as well, because it does inform the machine learner how much of that cost evaluation is real and how much is fluctuations due to noise. And so it can often use that information to do a better prediction on what point to do next.
Yep, so we have a question about Bayesian optimization. How does this compare to Bayesian optimization techniques?
Yeah, so we have a variety of different learners available. One is called a Gaussian process, and that's sort of a traditional Bayesian way of optimizing a multivariable system. So that's our Bayesian technique. But we also have some machine learning based options, including a neural net, which I mentioned before, which uses a deep neural net to kind of create a model between your system, the parameters and your cost. And we'll soon actually also be adding reinforcement learning. So we have a variety of options which fit in either the Bayesian category or the machine learning category.
Yep. One more question I see. Is the closed loop optimization approach part of your firmware layer, or are these two independent products?
Yeah, so the feature I'm talking about today is all available in Boulder Opal, and Boulder Opal has many features which, yeah, you can integrate into your stack just above your hardware level, which we call the quantum firmware level. But yeah, basically we're not announcing a new product today. It's all available in Boulder Opal. So if you already have a Boulder Opal subscription, this feature will be active for you right now.
Oh, I see we got one more question. How can you get more student investment in computing quantum technologies, in upcoming quantum technologies?
That's a good question. I guess we actually, in a separate presentation in the future, maybe a few months from now, we're going to be launching our product Black Opal. Black Opal is really our new educational product, which is targeted at a broader audience. So stay tuned to QControl and sign up to our webinar series to hear more about what we're going to be doing in that space.
Yep. And another interesting question, is a model of the system ever required?
Yeah, so there's like the broader question there is like, if you have a model, do you want to use it? so if you do have a good model of your system, often then you can use our optimization package, our model-based optimization package, and that can provide you an opportunity to get pulses and solutions quicker. And then typically you could then calibrate those pulses, which I'll show later, with this optimization package. But in the situation where you don't have a great model of the system, then in that case, no, you don't need one model at all, actually. The learner can completely figure that out itself, and it will learn that from the device. But the trade-off, there's always this big trade-off between using a model or not. And the big question is how much time do you have? Because if you do have a good model, you can make that calibration more efficient. But if you let this automated optimization routine learn it all itself, it will take a few experiments to get things running. But we've still managed to get things running in most of the experiments we've considered.
Yep. So we have a follow-up question for the input data. If you need to provide uncertainties, does that create bias?
So you don't have to. It's optional. But yeah, it's hard to know what precisely you mean by biased. So remember that we're not actually creating, the goal is not an estimate, the goal is to create an optimal set of parameters. So that the estimator internally is dynamically changing. I'm not sure, yeah, there's like the theoretical, there's the theoretical actual notion of biased estimation. I guess the challenge with also defining that for this is we don't actually have a model. So we're not doing parameter estimation here. So notionally, theoretically, asking is it biased is difficult to do. And then it's secondarily, the aim is actually to produce a control. And all we can say is that it does, we have shown, in simulations that it does converge to a control that we wanted to. Yeah.
Yep. So we have a question. How long does the learner take in general?
So yeah, it can take, so the demonstrations we've been doing can take on the order of hundreds of experiments to thousands. It just depends on your particular setup. But it is still, using our learners will typically be quicker than other out-of-the-box optimization routines like differential evolution or Neldermade, which we'll show in a second.
Yep. Is there a possibility to construct the model from input-output data?
Yes, so depending on the learners you're using, they will also provide a model at the end, so you can get a bit of a idea of what the machine learner currently thinks is going on with your experiment. This is particularly easy to do with the Gaussian process or the neural net. So yes, you are provided with a model afterwards. The accuracy of that model also, as always, it depends on like your data. So in regions where you haven't explored very well, that model doesn't necessarily give you a good place, but we often find that it does a great job of finding at least a local, it does a great job of finding a optimum, or a global optimum across the space, and then it gives you a good information about local minima around that. Maybe we've got a few more questions, but maybe we could, the next presentation,
yep.
And that might give everyone a bit more context as well. Great. So yeah, we'll get back to the rest of the questions in the next section. In this presentation, we'll present a series of case studies demonstrating how automated closed-loop optimization can deliver value across quantum computing, sensing, and communications. Our first two examples will focus on quantum sensing and quantum communication, and were demonstrated with mLoop in academic efforts that included myself and Harry Slatia, who are both now here at QControl. The last example we will show uses Boulder Opal and demonstrates how single qubit gates for quantum computing can be automatically calibrated. The first experiment shows how automated optimization can be used to create high-quality atomic sources for quantum sensors. Neutral atoms can be used to make sensitive measurements of acceleration and gravitational fields. These quantum sensors effectively drop a source of atoms and use quantum interference to measure their acceleration. The quality of these measurements depends on the number of atoms and temperature of the atomic sources. It has been proposed that a special form of matter, a Bose-Einstein condensate, or BEC, is an excellent source of atoms for these detectors. A BEC is a special form of quantum matter which forms when a gas of atoms is cooled near absolute zero, where all the atoms are in the same motional state. BECs have remarkably narrow bandwidth in terms of the atom's momentum. This results in high quality interference between the atoms, which can result in a higher sensitivity for a quantum sensor. Creating a BEC is done through a process of evaporation. Atoms are trapped with a combination of magnetic fields and lasers called a magnetic optical trap, or MOT. The potential depth is then slowly reduced over time to let the hotter atoms escape. The atoms that are left are now much colder. The height of the potential during this evaporation process versus time is called a cooling ramp. Determining the optimal shape of a cooling ramp is a non-trivial process involving quantum dynamics and nonlinear interactions. Typically, experimentalists have to manually calibrate the evaporation ramp each time they want to create a BEC. This makes it an excellent candidate for closed-loop automated optimization. The first experiment mLoop was used on was to optimize the cooling ramps to create a BEC. The experiment was completed by Wigley et al. On an experiment at the Australian National University. For additional details, please see the paper available in Nature Scientific Reports. The control parameters available to mLoop were a polynomial parameterization of the control ramps. The machine learner then ran a series of experiments where it attempted to create a BEC. The best way to quantify the quality of the BEC produced was to take an image of the atoms at the end of the process and measure the width of the distribution above a threshold density. This width was then converted to a cost that was fed to the machine learner. The machine learner then created a model of the relationship between the parameters of the ramp and the cost that was achieved using a Gaussian process. The machine learner was then able to use this model to pick the next best points to test to rapidly converge to an optimal cooling ramp. Here we show a comparison of the number of experiments it took for the machine learner to create a BEC compared to a previous work on automated optimization that used the Nelder-Mead algorithm. mLoop was able to find a BEC with a 10x reduction in the number of experiments after the common initial training runs. This experiment demonstrates that closed-loop automated optimization can solve complex control problems facing neutral atom quantum science experiments that are relevant to the production of better quantum sensors. The next example will show how automated optimization can improve the quality of components in a quantum communication network. Quantum communication promises to deliver a new type of information security that exploits the fundamental laws of quantum mechanics. A quantum network allows users to know if their communication line has been compromised by an attack. In order to build a quantum network at scale, it's likely we will need quantum repeaters that are able to boost the signal along these quantum networks. A key component of a quantum repeater will most likely be a quantum memory that can store quantum information encoded in light. A leading contender for a quantum memory is an atomic vapor trapped in a MOT, the same technology mentioned in the previous example. In this case, the efficiency of the quantum memory is directly related to the optical density of the atomic vapor. Increasing the atomic density of the vapor is a complicated challenge where the state of the atoms and the strengths of the magnetic coils have to be changed over time. Again, optimizing this protocol is a complex process involving quantum dynamics and nonlinear interactions. Hence, it is an excellent candidate for closed-loop automated optimization. An experiment was performed by Tranter et al. As shown here at the Australian National University. Additional details of the experiment are available in the paper published in Nature Communications. The control parameters were the strength of the lasers controlling the atomic state of the atoms and electronic coils controlling the MOT over time. The optical depth was calculated by measuring the amount of light absorbed by the atomic vapor of the MOT. This was then converted to a cost that was provided to the machine learner. In this case, the machine learner used an ensemble of deep neural nets to create a model of the relationships between the MOT control parameters and the optical depth that was measured. The neural nets were then used to pick the next experiments to do to find an optimal set of parameters. The machine learner was left to find a set of control fields that maximize the optical depth of the atomic vapor. The optimal controls of both the laser detuning that controlled the atom state and the trap coils that controlled their confinement are plotted here. We show both the best controls found by a human experimentalist and by the machine learner. What is particularly interesting about this experiment is that the machine learner was able to discover a completely novel control solution that beat the optical depth of any previous human attempt. We can see on the right the optical depth of the atomic vapor. The machine learner solution shows a significantly lower depth in the lower plot. This demonstration shows that machine learning-based automated optimization can discover novel control solutions that human experimentalists may miss. The increase in optical depth results in an optical memory with a higher efficiency, which will most likely be a critical component in a quantum communication network. The final example we will look at is calibrating a single qubit gate on a superconducting quantum computer. This example will use QControl's Boulder Opal and takes advantage of the managed cloud computation resources and batching feature. We have previously demonstrated that using QControl's robust pulses can improve the performance of gates on IBM-Q. Here we show the effective gate errors for X gates on IBM-Q run over 4 days. We can see the robust QControl pulses achieve up to a 10x lower error rate across a 5-qubit device and over about a week without recalibration. Normally, calibrating these pulses is a multi-stage process as shown here. The shaped pulses derived from a model-based optimization performed using Boulder Opal have to be rescaled when run on the IBM-Q device to account for imperfections in the hardware. The first step of the calibration is to measure the Rabi rate as a function of arbitrary units Qiskit OpenPulse gives access to. The next step is then to fine-tune the relative I and Q values, which define the control waveforms defining our robust pulses. This is done over multiple stages, where initially the relative amplitude between I and Q is scanned over multiple gate repetitions. Then the total amplitude of I and Q is finally tuned with scans again over multiple gate repetitions. This procedure can be scripted, but does consume a reasonable number of experimental jobs on the hardware, a valuable resource. Next, we show that the 2 final stages of this calibration process can be replaced entirely with the closed-loop automated optimization feature. The Boulder Opal automated optimization package is given control of both the relative and absolute amplitudes of the I and Q channels, and coarse information about the correspondence between the Rabi rates and amplitudes. A series of 10 batched experimental runs run with different parameters are then executed, where the machine learner is asked to find the optimal set of parameters. Batching permits the learner to make decisions based on measurements taken using a variety of previously determined test points. This approach ensures that we don't face a bottleneck in waiting for data to be returned from IBM's Cloud API, which is currently the slowest step in the process. Here we can see the optimal infidelity is found in only 4 iterations. The configuration parameters rapidly converge from their initial configuration at A to the final optimal set at C. We have provided 3 examples of using closed-loop automated optimization to improve the performance of quantum experiments with applications in quantum computing, sensing, and communication. We have shown how the closed-loop automated optimization package that uses mLoop and Boulder Opal can rapidly converge to an optimal set of parameters with a 10x reduction in the number of experimental runs compared to previous industry standard algorithms. We also demonstrated that the machine learning algorithm can find novel control strategies that human experimentalists may miss. And finally, we showed the bespoke complex calibration procedures can be replaced by an easy to set up and fast to run automatic calibration process. In the next presentation, we will explore how closed-loop automated optimization can be used to improve the performance of 2-qubit gates on IBM's superconducting quantum computers.
Yeah, thanks, Michael. So maybe we have a time for 1 or 2 questions, and then we can delay the rest to the end of the talk. So we have a question here. Are you able to model the system drift? So there's an example, for example, base the calibration at some time t on knowledge you have from the optimal solution in the past.
Yeah, there's 2 components to this question. So first of all, it's important to recognize at the examples I all gave there today, there's no dynamics per se. So you are sending a set of parameters and then you're getting a final cost at the end. So in all of those cases, what happens is if there is random walks or random drifts that occur during that process, that just basically comes out as some type of stochastic element at the cost at the end. And then yes, the optimization algorithms we use are robust to noise, are robust to these kind of errors, and they eventually form a better model as you do more experiments and find the average through that noise floor. In particular with the Gaussian process, it's basically also does an estimate of a noise process on top of the cost and uncertainties that are coming through. With regard to can you use knowledge from past optimal solutions and models? Yes, you can definitely seed your initial optimization with a previous solution you have. And then you can even, if you want, just add a question that was sort of in the previous runs was like, what information do you have about your parameters? The parameters you can have, you can provide us with minimum and maximum bounds. So you can, of course, provide us with a previous solution if you want. And then, and on top of that, simply put some parameters, additional variability you may want. So you can give it a good start, so to speak, and you can even bound the search around a previous solution that you have.
So maybe one question before we go on, is there a limitation to the number of the qubits?
So there's no limit, thankfully. And I guess one of the other really key advantages here is if you have a multi-qubit system where you begin to hit challenges where the dimensionality of that system is very large and it's very difficult to then simulate that on a classical computer, these techniques have a great opportunity to circumvent that, because you can still optimize that system, that multi-qubit system, which you can't simulate on a classical computer, because you're using a model-free approach here, which will still be able to find a solution. And in a sense, the actual experiment itself becomes your system that computes the controls you're trying to optimize. Great, so we'll just move on to the final section now.
Hey everyone. In this presentation, we are going to examine how closed-loop optimization can be used to improve the performance of multi-qubit gates on real quantum computers. When we think about the future of quantum computation, a clear end goal is to be able to run algorithms that solve meaningful problems. So why are we interested in two-qubit gates? That's because two-qubit gates are the most basic building blocks that generate entanglement in quantum circuits. For example, in this sketch of the VQE algorithm. Currently, the low quality of two-qubit gates is among the most limiting factors in achieving high-performance quantum algorithms, and therefore improving them is crucial. And why are we interested in black box optimization? Well, that's because model-based methods struggle on real devices. That's mainly due to the difficulty in describing multi-qubit systems with a simple physical model, and also as a result of noise sources that are often uncharacterized. This is demonstrated in the plot. You can see here the evolution of the qubits population in the presence of a drive. The solid lines are calculated from a simulation that assumes the model taken from the IBM backend, and the dots are data points taken from the real device. The exact details are not very important, but you can see clear discrepancies between the data and the simulation. The question that we want to answer today is, can we learn low-level implementations of two-qubit gates without having any physical model of the system? Before diving into the optimization process, let's quickly review the way that two-qubit gates are implemented on the IBM device. As most of you know, gates are implemented by electromagnetic pulses. Single-qubit gates are implemented by pulses with the same frequency as the frequency of the qubits they are addressing. To entangle the qubits, the first qubit, for example, is driven with the frequency of the second qubit. This procedure is known as the cross-resonance gate. On the right, you can see an example of the ZX gate as it is implemented on one of the IBM devices. The D1 channel is the resonant drive, while the U1 channel is the cross-resonance drive. The different colors in each channel represent the real and imaginary parts of the pulse. In practice, there is another resonance control of the second qubit known as cancellation tone, which I don't show you here. Now, when we understand how gates are implemented on the IBM device, we can turn to the optimization part. The basic idea of black box optimization is improving by interacting with the system. As we just saw, gates are implemented by electromagnetic pulses. We can represent gates by long vectors that, for example, store the real and imaginary part of each segment in a piecewise constant pulse. We then send the candidate gate to the device and evaluate its performance by collecting measurements and calculating a cost function. We then use that information in order to suggest a better candidate. This loop goes on until we find a satisfactory gate implementation. There are two key elements in this optimization process. The first one is the cost function. The cost function is not unique. A good cost function reflects the gate quality and returns lower and lower values as we improve the gate implementation. Since we are interested in the error of the gate, good cost functions wait out unwanted effects, such as state preparation and measurement errors. Finally, during the optimization process, we call the cost function many times. Therefore, it must be efficient. A possible cost function is randomized benchmarking. Unfortunately, it is not efficient enough in order to take part in the optimization process. Instead, we are using a repetition scheme, where we start from different initial states and apply the gate a different number of times. We choose the exact scheme such that all the points I just mentioned are fulfilled. The next ingredient is the black box algorithm itself. There are many possible algorithms. And while we do use and explore all the algorithms in that list, today I will show you results of 2-qubit gate optimization achieved with reinforcement learning and with a different algorithm that belongs to the simulated annealing family. If you are interested in more details, you may check our previous webinar where Michael presented the concept of reinforcement learning algorithms for optimization. Now for the results. Let's start with a simulation. Here we compare a gradient-based algorithm with a specific simulated annealing algorithm known as Cauchy machine. Remember that in the simulation, the Hamiltonian of the system is perfectly known and the unitary is fully observable. You can see that even under these conditions, the gradient-free method outperforms in the presence of noise. On the real device, where the model of the system is not accurately known, the gradient cannot be easily calculated, and there are different types of noise, we do expect the gradient method to struggle even more, while the black box methods to perform as well as here. Finally, let's see results from the real device. Here you can see the progress of the optimization process, in this case simulated annealing, on the IBM device Casablanca. Our starting point is the IBM default pulse. The plot shows the cost function versus the optimization step. Notice that, unlike in many gradient methods, the cost function can also go up as we explore new pulses, or stays the same for a while as we look for better candidates. When we are satisfied with the cost value, we take the final pulse and test it against the IBM default pulse. Here you can see the error of the ZX gate versus the number of its applications. The blue line is the IBM default pulse, which is recalibrated on a daily basis. The purple curves show the QControl optimized pulses as we got from two different methods. In the upper plot, the simulated annealing algorithm, Cauchy machine, and in the bottom plot, the reinforcement learning algorithm, policy gradient. To the right, you can see the gate schedules for the optimized pulses. Notice that for a single gate application, the spam errors dominate the performance, and the different implementations cannot be separated. However, for more applications, performance gap opens. We can extract and approximate gate error from these plots. And as you can see, both methods produce over 2x improvement over the default IBM pulse. Here you can see similar results on a different IBM device, Bogota. While the improvement here is not as big, it is still significant. To complement the repetition experiment, we ran an interleave randomized benchmarking experiment with a CNOT gate we constructed from the QControl optimized ZX gate. And we compared that with the IBM default CNOT gate. As you can see, the results are consistent with the repetition plot. the error of the QControl optimized CNOT gate is about 1.6 times better than the IBM default. Remember that the IBM CNOT has an extra control, the cancellation tone, and the benefits seen here were achieved without including this control in the optimized pulse. So what's next? Clearly, we want to keep improving the gate fidelities, which may be achieved with shorter or more complicated pulses. More importantly, we want to go beyond gates and show improvement in small-scale algorithms. These charts show simulation results of an optimized variational quantum algorithm that aims to solve a specific optimization problem. As you can see, using optimized gates increases dramatically the success rate of the algorithm. The next step is to leverage our black box optimizers and achieve similar results on a real quantum computer. And one last comment before I finish. At QControl, we understand that there are users with a variety of backgrounds in quantum computing. And many users want to leverage the capabilities we've just shown here today, but don't have any hardware expertise. We're happy to let you know that the automation capabilities we discussed today will form the backbone of Opal, our forthcoming product for quantum computation end users and algorithm designers. Opal is a critical product enabling abstraction of the hardware while still delivering improved performance on cloud quantum computers. We're excited to be able to bring our expertise in quantum control to an increasing diversity of users. So please, stay tuned.
Great. So we have a few questions popping up now. First, is your closed loop optimization method applicable to annealing parameters?
Yeah, so in general, as long as you can define a task and a good cost function for this task, and as long as you understand what are the knobs or the controls that you want to optimize for, you can use these methods. The exact problem that you're trying to solve is less important.
And next question is it possible to select experiments from a specific corpus of possible experiments, such as Rabi or Ramsey, with a disjoint set of input parameters, or must all experiments be globally parameterized?
Yeah, so there is no constraint there. So I think it's quite similar to the previous answer. As long as you understand what are the controls that you have and what are the knobs that you can control, and as long as you have a good cost function that capture the task that you want to optimize, these methods can work.
Yeah, and I guess a good example is the quantum memory, where we were controlling both laser strengths, magnetic coils, all simultaneously and sort of in a disjoint manner. So yeah, anything can be handled.
Yeah.
Next is how you can, what is the starting cross resonance waveform for that for the experiment you had?
So yeah, I think I mentioned that in the presentation. So typically we start from the IBM default as our starting point, but in general, you can start from a random pulse as well. Yeah.
And I guess the other kind of relevant question on IBM, so how much runtime do you need to reserve on Casablanca to get a decent pulse?
Yeah, so that's a great question. So indeed, we are using cloud quantum computers, which are typically quite large overhead. So these processes can be quite long. So just to give you some idea, to start to get good results, we typically need around 30 minutes. And to get the best results, for example, on Casablanca, it can even take 2 hours. But if you have access to your own hardware, it can be dramatically faster. Just to give you a hunch, in the simulation, where we use exactly the same structure as on the IBM device, the whole procedure is under a minute. So that's a huge difference between 2 hours and a minute. And probably if you have direct access to a quantum hardware, it won't be a minute, but it would probably be much closer to the minute scale and not to the 2 hour scale. So that's a huge improvement.
Another good question is, how can you be sure to reach the global minimum and not get stuck in local minimum?
Yeah, so of course there is no guarantee, but one of the advantages of these methods, whether it's the simulated annealing or evolutionary algorithms or the RL, is that they can deal much better with local minima compared to gradient methods. So of course, in the end, there is no guarantee. No one can prove, I mean, unless you get 0 error, and then you know that you're in a global minimum. But these methods are typically explore enough such that many times you can go uphill as well. And I think we saw that in the plot of the cost functions, that many times you just go up because you explore and try new regions.
Great. So next question is, what does no cancellation tone mean for optimized pulses?
So it just means that we used only one channel for the optimization, only the cross-resonance channel. But typically, you can use more channels, and in general, more controls can give you better results. Of course, at the price of harder optimization problems. So definitely, right now, we're also exploring this option of adding more control and see if we can get even better results. But on the other hand, also getting good results with less controls is favorable.
Yeah. Okay, so we've also got another question from Daniel. If you manage to factor 2 improvement, does this mean you will try to win the Open Science Prize competition? Or does your factor 2 not count because the spam error is dominating?
Yeah, I mean, we are definitely interested in other gates like swap. I'm not sure if, yeah, we'll try to compete there.
Yeah, I'll make the comment that like we are definitely, stay tuned to QControl. We're definitely going to be making a statement about what our gates can be doing in the context of that competition. There are some details in the competition which we're still investigating the exact conditions of what it means to enter. But the other thing I just highlight here, the factor of 2 does count. So the spam error is just related to how you're doing that measurement. And the point is randomized benchmarking or other repeated techniques allow you to see the real error noise above that spam error. So yes, the factor of 2 is valid because we've verified it using randomized benchmarking. Got a nice one here. So finally, what Marina's asking, so finally, what exactly is optimized? So what part of the system optimized? So if the Hamiltonian is still noisy, what has been fixed, and what way is the information that you read out? Are we optimizing the information reading out, or information estimated errors on the noises? What are we actually optimizing here?
Yeah. So actually, we don't need to think about Hamiltonians. The model of the system is not very important. We're optimizing the controls that we have. In this case, the gate. So it's the cross resonance channel. We're considering piecewise constant pulses, and in each segment, we have real and imaginary part, or R and Q part of these. And these are the parameters that we optimize.
Yeah.
And the cost function just give us the quality of the gate of our implementation. And we're just using this knowledge in order to suggest better and better candidates until we get a good performance for the gate.
Yeah. Michael's saying, is there any advantage over using QDITs over qubits? I guess that's just a sort of a more general question. I would highlight that the superconducting devices are actually QDITs, so they have extra levels. And I think the other thing is we have to take that into account. We've found when we've been doing these optimizations. Okay, so then what we have. Okay, we've got quite a few questions coming through, but we're beginning to run out of time. So what we'll do is we'll keep answering some of these questions that are left behind. But for those who want to have a further discussion with us, you're welcome to. So I'm about to post a link. So in the chat, I just posted a link. You can click on that right now if you'd like to set up a call with us. It'll send you to Calendly, where there'll be a bunch of times available, and we can continue this conversation that we're currently having in the Q&A. Also, again, once we finish this webinar, you'll be invited to fill out a survey. I would really request that you do, and you go into a chance to win a $50 gift card, which we really appreciate. So let's just answer a few more of these questions. So we've got a question from Kevin. How many parameters are usually used in your tune-up in your calibrations? Is it on the order of 5, 50, or 500?
Yeah, so in our case, it was an optimization problem and not exactly calibration problem. But we use 20 parameters. If you want to use more than one channel, then it can be 40 or 50 parameters. It depends on the exact algorithm that we use. But in general, definitely these scales of parameters of 40 or 50 is absolutely doable. If you want to go to a few hundreds, it's also doable, but probably needs some more work. Yeah.
We've got another question. Does it boil down to solving continuous optimization? This can be a hard problem itself.
Yeah, so I mean, we do it as well. Some of the algorithms that I didn't show you today that we explore currently, for example, like for those of you who are familiar with the soft actor critic algorithm for reinforcement learning, they deal with continuous problems. So yeah, that's definitely something that we are exploring as well.
Okay, so next one is, can you give examples what we learned from the pulses generated using machine learning method, and how does it improve the design of devices?
Yeah, that's a good question. So ideally, we hope that the learner figure out a way to avoid unwanted effects, such as leakage to higher levels, such as crosstalk that you have in real devices. It's not necessarily very easy in the end to take the final waveform and try to understand exactly what happened, but that's definitely something that one can try and learn how the agent or how the algorithm learns to overcome things like leakage, such as crosstalk or other things like that. Yeah.
We have another question which relates back to that simulated one, and it's related to DWave. So do you think that our optimization approach has relevance to DWave? And do you think it could expand some of the applications in that device?
So I think absolutely. These type of optimizations are very robust. They can deal with a variety of problems. And again, as long as you have good understanding of the controls that you have and the knobs that you have, and a good task with a cost function, they're extremely robust and extremely flexible, and you can use them to discrete, to continuous problems, to gate optimization, to gate calibration, to improving other types of problems. So any optimization problem can be approached in this black box manner. Yeah.
Yep. And then finally, could you comment more on the cancellation tones? How are they implemented, and why are they considered costly?
Yeah, so maybe I can just say one thing. One of the problems in these devices is the phenomenon of crosstalk. So when we drive one qubit with the frequency of the other, some of it leaks to the other qubit, and then the other qubits see it as a resonant pulse. So ideally what you want to do, you want to cancel this effect of leakage. So if you have all the parameters and knowledge about the crosstalk in the system, you can exactly construct the pulse, which is the opposite of the part that leaks, and then you can correct for it. Of course, it's very, very hard to characterize exactly the crosstalk in the system, and therefore designing very accurate and good cancellation tones can be quite hard. And hopefully, the black box can find a way either to avoid to begin with or to lower dramatically the effect of crosstalk. And if we'll add this channel as part of the optimization, I can find a way to, in some sense, cancel the effect of crosstalk in the system.
Great. So once again, thank you everyone for attending this webinar. We'll leave it there with the questions. If you have any more, please hit that link in the chat or in the email to set up a call with us. And of course, please subscribe to our webinar series, and we'll have further presentations with more work and new features we're releasing in Boulder Opal, as well as, of course, more discussion about Fire Opal, which we talked about at the end, which is a new product which was really going to be incorporating a lot of these solutions that we talked about today, so that you can see these improvements on real devices. So thank you, everybody.
Bye-bye. Thank you.